all this stuff because the disjunction and the conjunction comes into play when we turn the page and see what is now introduced into the problem that wasn't before. What do we see now? Absolute value. So we got to slow down. And above, at the top of this page, dis union greater than ors. Dis union greater than ors. Here is the process. Numero uno. We must have the bars isolated, just like it was before. The bars must be all by themselves on one side of the symbol. Are they in number 17? Yes. Then look to the symbol. Is the symbol a greater than or a less than? It doesn't matter if they have equal to bars or not. Is it a greater than or is it a less than symbol? Less than. So, if this union is greater than or, this will not be a disjunction. It will be a what? So let's put above each problem, it will be a conjunction. Will it be a union or an intersection? Intersection. And then you don't need the symbol because that's already in there for you. And what will be the word, my friends? And. This union greater than ors, since the symbol was a less than, it doesn't qualify with any of those. It is not a disjunction, it is a conjunction. It is not a union, it's an intersection, and it's an and situation. Sound okie dokie smoky. So here's our process. We have isolated the bars. We have identified what's going to happen. Now we split it up into two scenarios, very similar to what we did before. We'll take what's in the bars, 3x plus 4, and what you see is what you get. What you see is what you get. I put the less than symbol because I saw it, and I put an 8 because that's what I saw. The first one is what you see is what you get. The second one, what word will we use, my friends? And or? We will use the word and. The second one is what's in the bars, 3x plus 4. But you switch the symbol, switch the sign. Isn't that a less than symbol? It becomes now a greater than symbol. Isn't that a positive 8? So it will become a negative 8. Sound okie dokie with you? Okay? Two situations. Don't worry that that's a negative number. There's no bars involved anymore. We just want to solve each of them. So let's solve the red one together. Any questions on the setup so far, though? Red one, first move. Subtract 4. Right? And those of you who have never had me before, you got to get over your fear of fractions. You've got to get over your fear of fractions. Not everything will come out nice. Isn't the next move to divide by 3? So what will we get? 4/3. And we didn't have to switch a symbol. Don't put 1 and 1/3. I hate compound fractions. 4/3. Well, punch it in if you need to figure out what it is as a decimal, and let's find it on the number line and locate it. Where is 4/3? Between what and what? Between 1 and 2. It's 1 and 1/3, so here's 4/3. Helper arrow. Right here. That's the red situation. You've got to have that 4/3 on the number line so we could tell. Let's go blue now. Solve the blue one. You only switch the symbol when you multiply or divide by a negative. We divided by a positive 3, so you do not have to switch the symbol. Cool? Graph the blue one. Awesome. Then you got to go back up to your words up here to help you. This is an and situation, which is an intersection. I need where the red and the blue are on top of each other. Where the red and the blue are on top of each other. And so let's do that. Let's graph that final on our number line. -4 does not count. Right? Not count, because it's got to satisfy both of them. For an and situation, if you get cookies and ice cream, didn't you get both of them? You got cookies and ice cream. If you get cookies or ice cream, couldn't you just have one of them, you know? But and means it's got to satisfy both of them. -4 does not satisfy the blue, so it does not count in the and situation. It's got to come open. Same thing here. Isn't this open at 4/3? So where's the intersection? On the outsides or on the insides? It's in here. Isn't this where red and blue are on top of each other? right there. That's our final answer right there. Whew. Yep. Let's write this in set notation. This is an AND situation, compound inequalities. So it's the set of all variables that we are using, and isn't it an X in this situation? Such that. AND is the compound inequality. X is in the middle. Smaller number on the left, bigger number on the right. Smaller number, reading from left to right, doesn't it go from -4? Symbol points to the left every single time. No equal to bar, because that's an open dot. X is in the middle, points to the left, 4/3. Come on, pen. And then we close the brackets. Set of all x, such that x is less than -4 and at the same time less than 4/3. To read that out loud, that has to be read from the variable each time. It's the set of all x such that. Then I said this, x is greater than -4, and then I said this, and at the same time, x is less than 4/3. That's the hardest ones to read right there. Step 1 in any absolute value situation is to isolate the bars. First move we had to do on 18 was subtract 1 from both sides, and we get this. Now that the bars are all by themselves, we must figure out the word we want to use. The word helps with this phrase, this, union, greater than, or. What is the symbol in this bad boy? Greater than. What word will we use then? Or. So I will write dis, union, and or. You need to tell me that it's a disjunction. That's part of like the problems, like this is a disjunction or a conjunction. Well, this is a disjunction. You need to figure out what word you'll use and a symbol so we can graph that together. So the bars are all by themselves. Now let's set up two situations. First situation, what you see is what you get. We'll drop the bars. 4k greater than 26. I personally put the symbol. I don't put the word anymore. I put the symbol, union. You could put the word or. It doesn't bother me. But I'm going to say in union with. What you see is what you got for the first one. The next one, you switch the symbol, switch the sign. Notice the symbol became switched and the sign became switched. Sound all right? Solve the blue one. It turns out to be k is greater than 26/4. 26/4. Can 26/4 reduce? 13/2. 13/2. You can always punch that in and figure out what that is as a decimal. Isn't that 6.5? So I'll find that right here. That's about right, meow. And I will put 13/2, not 6.5, and say, red situation. Get that solved. I'm doing a lot of work for you. I'll let you solve the red one on your own and graph it. Is it a union or an intersection? Union means what you see is what you draw, right? Draw it all. Draw it all on your final. So it goes from here over, and it goes from here with an open dot, my bad, over. United them together. Put the red one and the blue one together. Well, that's what I'd get when I put the red ones and the blue one together. Set notation is easy on ORs. What you see is what you write. Set of all k's. Such that. Then I take this guy and put her in there. Set of all k's such that k is greater than 13/2. The word is or. K is less than -13/2. Now get that in interval notation for me. Negative infinity. That's fine if you say negative infinity. From negative infinity, non-inclusive, to where? -13/2 with a parenthesis. Symbol. Then from 13/2 to infinity. Nothing was included. Cool. One more easy one. Number 19. Step 1. What's step 1 in absolute value situation? Isolate the bars. Are they isolated? Yes. You and partner, give me words. I need a disjunction or conjunction, union and intersection, and or. Write them right above there. Right above there. Once the bars are all by themselves, figure out what you need for information. This is a less than, correct? So what I want above there is conjunction, union or intersection. What is it? Intersection, and or. And. Now, let's solve. Let's take what's in the bars. And what you see is what you get. And take what's in the bars. Switch the symbol, switch the sign. Switch the symbol, switch the sign. Solve one, graph one. Solve the other one, graph it. So I solved them both, and I graphed them both. And now you have to talk yourself through it. What are we doing? Union or intersection? Intersection. So that's where they're on top of each other. From where to where? From here to here. Isn't that where they're on top of each other? So we graph that as a final down meow. And that was included in both of them. See if you can get that to me in set notation. That's a compound inequality. Compound inequality, where the variable's in the middle, right? And we got those symbols pointing to the left. Try that in set notation for me. In the middle. So I just do it from left to right. The variable's in the middle on these and situations. So from the left, I have a -4. Which way should this symbol point? To the left. And there is an equal to bar. Then I put my C in the middle. The symbol again points to the left, and I put my equal to bar and put my 16. Interval notation is a breeze. Isn't interval notation much better than set notation? Let's skip 20 and go to 21, and let's get nuts. 21. I think that's where I wanted to go. Yeah, 21. Remember the old common sense checks, right? The old common sense checks. What do you feel about a common sense? Are the bars all by themselves? Yeah. Then they want to say when this will be greater than 0. When do you feel that absolute value will be greater than 0? Will it always be greater than 0? Do you feel that? What do you think? What's the absolute value of 0? It's 0, and is that greater than 0? So my common sense first said, hey man, shouldn't absolute value always turn out to be greater than 0? It's like, yeah, but it can also turn out to actually be 0. Isn't that true? So what if that had a equal to bar with it? Then we'd have a different situation. Cool? So this one we have to solve. Okay? We got to solve. Are the bars all by themselves? Yes, they are. So we will do two situations. We will have -4x plus 8. What you see is what you get. Oh, I guess we need our words. This is a greater than symbol. So if we do disunion greater than ors, what is this situation? Disjunction, union, and an or. Disunion greater than or. Because that symbol was a greater than, all those words apply. And now we'll put or in there, or the union symbol. I don't care what you put right there. And we'll have our two situations. The other one, we switch the symbol, switch the sign. You can't switch the sign to 0, but you can still switch the symbol. Okay? So let's solve them both. Solve the red one, graph it, and stop, I should say. Solve the red one, the one on the left, and graph it and stop. So we had to switch the symbol because we divided by a negative. X is less than 2. Cool? Now solve the other one. Subtract 8 again. -4x less than -8. Not quite the same thing, because when we divide by a negative, what do we got to do? Change the sign. That becomes x greater than 2. So watch me graph that. That'd be right here. Right? Nice and separated. That's x greater than 2. And this is a union situation. Correct? Then we got to put it all together. So how far to the left will it go? -infinity. How far to the right will it go? But we got to put these together, and what happened right there? Didn't we get a hole on top of a hole? Does 2 count in this situation? 2 didn't count on the red one, did it? Did 2 count on the green one? So when we bring that down, boom, we got a big hole right here too. But we go here, and we go here. And it's like every number in the world worked, except for one of them. Which one didn't make it work? 2. So this is an OR situation, set notation, set of all x, such that what you see is what you write with the word OR in the middle. What you see is what you write on x's. So give it a shot. You just put these 2 in there. Those were our 2 answers that we had. X could be less than 2 or x could be greater than 2. Sound cool? Interval notation. Far left, negative infinity. Then I'm going to follow. Remember, I'm only looking at this green graph right here. Went from negative infinity. Boom! Isn't there a critical spot right there at 2? So it went from negative infinity to 2, and 2 didn't count. In union with, where did it start up again at? 2, and 2 didn't count. To infinity. Why is there a hole in the graph? Because guess what we get if we put 2 in right here? What's negative 4 times 2? Negative 8 plus 8, which is how much? We'd get a 0 in there. And that's the only time when this wouldn't work, when this turned out to be 0. Everything else would make it true, because you all told me that that was the situation that didn't work. But if you have a negative number in there, that will still turn out positive, and etc. So, hey, man, almost everything worked. Again, is it the same problem over again? Almost. Are the bars by themselves? If this number is 0. Common sense check, though. Is there an equal to bar also? Common sense check. Will absolute value always turn out to be greater than or equal to 0? Yes. Doesn't matter what's in here. Once you turn it out, it'll turn out to be either 0 or positive. Correct? So, how many numbers work? All real. So let's graph that on the number line right away. I don't have to do any work. This is a common sense check. Because of the equal to bar. Because of the equal to bar, that helped us. All reals is the whole mamma jamma. Ba-choom, ba-choom. Set notation. I'll say it. You write it. Set of all x such that x is an element of the real number system. Isn't that our variable, x? Is that right? Yeah. Set of all x such that x is an element of the real numbers. And then in interval notation, it goes from negative infinity to positive infinity. My friends, common sense. Isolate the bars, then determine about common sense. Okay? Let's try it again. Holy schmackaroni, 23. What's this first step? Isolate the bars. This is going to be nasty right here because of that variable outside the bars also. So isolate the bars. Can we do 2 things at once? Would you agree that this has to move over? So you do what? Minus 1. You have to move that over, so it would be a plus x also. So you have absolute value of x. Symbol stays the same. X plus 1, or minus 1. Cool? Bars are by themselves. Dis, union, greater than, ors. Does that satisfy this situation? It's a greater than symbol. So dis, union, greater than, ors. Both situations. We take what's in the bars. And what we see is what we write. Cool? Word is or. Take what's in the bars, switch the symbol, switch all the signs. That would become a negative x. That would become a plus 1. You okay with that setup? The blue one's crazy. The blue one's crazy. Like I said, this gets nasty. What's the move? Well, we got to get all the variables to the left side. And when you subtract x, isn't that the right move? What's x minus x? It's 0. It's 0, baby. And that's what you're left with. 0 greater than negative 1. Right? Well, When the variables disappear, you got to ask yourself true or false. Is 0 greater than -1? True or false? 0 is greater, so this is a yes right here. That means if we want to graph this, you graph all the numbers. That's all real situation right there. So there's the blue graph right there, all reals. The green graph we got to solve. Don't we want to add x over here, right here? So we get 2x less than 1. Is that correct? And then the next move is divide by 2. X is less than 1/2. 1/2 is right here. And it would be like this. And what do we want? Union or intersection? Union. So we put it all together. It's the green one plus the blue one. And the blue one had everything in it, correct? So what do we get? Everything. All reals. And then we'll handle the set notation, interval notation. I know you can handle that. Let's kind of move on, okay? Next one. Are the bars all by themselves? Yes. See this number being 0? That's where I try a common sense check. Will absolute value always turn out to be less than 0? What do you think? Will the absolute value always turn out to be less than 0? That cannot happen. That cannot happen. Absolute value will either turn out to be 0 or positive, correct? Boom. Empty set. You got to put something on the graph for me, right? On the graph, you put nothing. But you can't just leave it blank. It looks like you didn't do it, so put empty set right next to the graph. Put it in set notation. Boom. Empty set. Put it in interval notation. Boom. Empty set. Done, 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 done. Sound cool? Next one. Let's use a common sense check. First, I can't do that on 25 because are the bars all by themselves? No. So should I distribute that -2 through? You cannot distribute through absolute value bars. You will divide by negatives, right? You will divide by a negative. So if I divide by a negative, though, what happens to that symbol right there? And that becomes a -6 right there. Cool? That becomes a -6. Now, it's all about zeros, right? Let's think about this. Zeros or negatives are weird. Will absolute value turn out to be greater than or equal to -6? Because absolute value will always turn out to either be 0 or a positive number, correct? So absolute value coming out greater than or equal to a negative, won't that always happen? So how many solutions do we get? All real, correct? All real. And then on the last one here, are the bars all by themselves? I understand you can do set and interval on your own. Are the bars all by themselves? So isolate. We get rid of that times -1 by dividing by -1. That switches the symbol. Correct? That switches the symbol. Absolute value less than a -4. That will never, ever, ever happen. The absolute value cannot turn out to be less than a negative. So here's the common sense checks. When this number over here, when the bars are by themselves, is either 0 or negative. 0 or negative, you have to start asking yourselves the question, will this ever be less than this number, or will it ever be greater than that number? This can't happen. So boom, 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 boom. Now, if you wanted to go through and do all the work, you could do it. You could have graph this one, and ask them, and they would never intersect, or they would never unite, or something like that, or they would always unite. But common sense check, my friends.
So let's put this to the test with some story problems. Let's actually use this for something. So here's a story. A carpenter is using a lathe to shape the leg of a table he's making. In order for the leg to fit properly, the leg must be 150 millimeters wide. But there's a margin of error, sometimes called the tolerance, a margin of error of 2.5 millimeters. So write an absolute value inequality that models this relationship and find the range of width the leg can successfully fit. Well, obviously, it's really not that hard to do this just mentally. You know, it's like, all right, if the leg's supposed to be 150 millimeters wide and you got a tolerance of 2.5 millimeters, you just add 2.5 and subtract 2.5, and it's like there's your range of values. But they want us to write an absolute value inequality, so here's a basic formula that I think you should write down on your sheet here. The formula for these tolerance problems will always be the absolute value, so you can see the bars here, of x, which x is the variable we'll define in each problem, minus the given value. That absolute value will be less than or equal to the tolerance. And this is really the magic. The easiest number to figure out here is the tolerance. So after we've got that copied down here, let's kind of define some stuff here. It's like, what is x even standing for? It's like, what are they asking us to find here, you know? X would equal, it says, find the range of widths the leg can be, so it's the range of widths the leg can be. X in this problem would be the range of widths the leg can be. And honestly, in this inequality here, there's only two things you got to know, numbers-wise, the tolerance and the given value. Well, the easiest thing to figure out is the tolerance. So it says if the margin of error, aka the tolerance, is 2.5, then 2.5 is the number that goes over here, meaning the other number that they provide us, the 150, that's the given value. One thing we better double check is that they're in the same units here. So this is in millimeters and that's in millimeters, so we're good. So our equation will be the leg, if we take away 150, come on pen, sorry. So x minus that given value in absolute value bars, that should be less than or equal to the tolerance, which is 2.5. So that's the absolute value inequality that we'd write for this situation. So to solve it now, we kind of ask ourselves, are the bars by themselves? Yes, they are. So does this union greater than or fit? Nope. So this is a conjunction, which is an intersection, which is an and statement. And now we'll solve. So we'll take what's in the bars, x minus 150, and what we see is what we get. Throw the old word and in the middle, and then we take what's in the bars, and then we switch the symbol, switch the sign, and then we solve both of them. So let's go solve the blue one. What do we do to solve this? Well, we add 150 from both sides, to both sides I should say, and that would give us 152.5. And let's just talk about this for a second. It says the x, like the width of this table leg, has to be less than or equal to 152.5 millimeters. Then over here, when we solve this other guy, x, we add 150 to both sides. Negative 2.5 plus 150 would give us 147.5. It also says at the same time that this table leg right here has to be greater than or equal to 147.5. So let's put that in set notation. It's the set of all x's such that, since this is an and statement, x goes in the middle, the symbols point to the left each time. We can actually have equal bars. So this is 147.5 and that's 152.5. And now let's answer this in a complete sentence. X is what we're talking about, and it's the table leg. So the table leg must measure from. From is a good word because from means you can include that has equal to bars. If you didn't, you'd use the word between. You know, between means these boundaries don't count. From means they do count. So the table leg must measure from the smaller boundary to the larger boundary, and then the labels were in millimeters. So again, it was a pretty obvious situation. You didn't need to set up an absolute value inequality to like figure that out mentally, but that's what these problems are all about, so let's do it again. The weight of each fountain pen manufactured in a factory must be 10 grams with a tolerance, boom, they tell us a tolerance of 2 grams. Pens that are not within the tolerated weight must be thrown away. So write an absolute value inequality that we can use. First, let's define x. X equals, like, what's the weight of the pen? Isn't that what they're talking about? So the weight of the pen. And then our absolute value inequality, we'll take that weight of the pen take away the given value. Is the given value 2 or is it 10? Well, remember, the tolerance is the number that goes out here, and it tells me the tolerance is 2, so the given value is 10. That will always be less than or equal to your tolerance. And then we'd solve both situations. So this is a AND statement again, because the bars are by themselves, so it's a conjunction, which is an intersection, which is an AND statement. And then we'll set up both of them. And again, you probably had that figured out mentally before you'd even go through all this work. But switch the symbol, switch the sign. X has got to be less than or equal to 12, and at the same time, X has got to be greater than or equal to negative 2 plus 10, which is 8. So in set notation, it's the set of all X such that, remember, X is in the middle, symbols point to the left every time. We are using equal to bars, smaller number, bigger number. It says the set of all X such that X is greater than or equal to 8 and X is less than or equal to 12. Close that bracket up. And then let's write our answer in a complete sentence. So this to me is talking about the pen's weight, right? So the pen must weigh from 8 grams to 12 grams. Capital letter, period, makes it a nice complete sentence. One more. Why don't you pause the video and see if you can get this bad boy set up on your own. So remember, we got to define our variable. X is the weight of the box, what they're talking about. Here's my absolute value inequality, because 1.2 is the tolerance. And then I realize it's a conjunction and an AND statement, so I solve them both, as so. Write it in set notation for an answer. Set of all X such that X is greater than or equal to 23.8 and less than or equal to 26.2. And then, of course, answer the question in a complete sentence, talking about the box must weigh from, because we have equal to bars, 23.8 ounces to 26.2